Okay, well, good morning and happy Friday, and happy, or what do I say? May the 4th be with you.
Yes.
Okay. All right, and we are talking Markov chain. Well, we were talking about Markov chains, and now I guess we can talk about Markov chain Monte Carlo. And so just a quick recap of Wednesday. We said if you have some states, okay, we could have a chain with two states A and B, where A can return to itself and B can return to itself, and we have a transition probability of one going from one to the other. We said we have some matrix P of transition probabilities, and this is the probability of basically A to A, and this would be the probability of going from A to B, and over here we would put the probability of going from B to A, and then lastly we would put the probability from B to B. Okay. And depending on, this is like bringing triggering my morning. It's like causes you to shudder. Okay, we could say if we labeled these like instead of states A and B, we could call this like 1 and 2 and 1 and 2. And we might also rewrite this as probability 1, 1, probability 1, 2, probability 2, 1, and probability 2, 2, to kind of indicate that, let A equal 1 and not B1, but let A be called state 1, and let B be called 2. Okay, and so, in some kind of, we were talking about transition notations and stuff, I could just kind of like write P11 or P21, and you will know that this is the probability from moving from state 2 to state 1. Okay. And we said that as long as the chain is aperiodic and irreducible, okay. If the chain is aperiodic means certain states can show up at it, other states. Generally, a chain will be aperiodic as if it's possible for one state to go back to itself. So as long as kind of these diagonal elements, as long as one of them is not 0, then it will be aperiodic. Okay, and if it's irreducible, then that means you can reach any of the other states from any of the other states. Then the chain will eventually converge to its stationary distribution. Regardless of its initial state. Okay, and I think we illustrated this very briefly on Friday. I said, here's some transition matrix, and then if I take this vector of kind of the current initial distribution, and then we apply the transition matrix, we can see what proportion ends up where. I hope this feels kind of familiar. All right, and there is a cool diagram. It actually shows up under the eigenvectors and whatever. Okay, so here is, this is supposed to represent you can, how do I? Okay. Anyway, so this this represents. We're gonna say we have two states, California and New York. Okay, and we can say if you're in California, you have a, I don't know, 9%. How do I edit this? Okay, all right. We'll say you have an 11% chance of moving to New York, and if you are in New York, we'll say you have a 30% chance of moving to California. Okay? Here, let me, actually, if I just reload this, it'll be 10.1 and 0.3. Okay? 10%, if you're in California, you have 10% probability of moving to New York. If you're in New York, you have a 30% probability of moving to California. Okay? And what this will look like is, so I'm gonna, what you will see here is these dots represent people in California and New York, and at each cycle you will see 10% of the dots in California represented in blue on the left go to New York, and you will see 30% of the dots in New York move to California, okay? And it's hard to see right now, but as this cycle continues and continues and continues, it eventually reaches a state of equilibrium where the number of dots going from California to New York equals the number of dots coming from New York to California. Now we can arrange this in some other way, okay? And this will be our initial state where New York has, 40 million and California only has 1.6 million. And when we hover over this, we will still see about 10% from California going to New York and 30% of New Yorkers coming to California, okay? So in the beginning, there's not even enough for one to go over. And then as it goes over, we see that the proportion will change until we reach a certain place of equilibrium where the number of people going from California to New York equals the number of people coming from New York to California, okay? And once it reaches this point, this is known as the steady state, or the stationary distribution, or whatever you want to call it, okay? And if we started off with everyone in California, okay, 10% go to New York, and now 30% of New Yorkers come to California, and so on and so forth, until we reach a point of equilibrium, okay? If we want to make it a little bit easier to kind of count and make sure that the dots indeed are, so we got 3, and then, we'll reach a point of kind of the number of dots going from California to New York equals the number of from New York coming to California. Okay. So that's kind of neat, right? And then, if we change these things, and I say, all right, now 60% of Californians are going to go to New York and 30% of New Yorkers come to California, then we can see how this will change the equilibrium place, okay? Or now the equilibrium is where there are more people in New York, okay? All right, so how do we find the stationary distribution, okay? All right, does that make sense? The kind of the stationary distribution? Okay. Stationary, okay, and the stationary distribution is where the stationary distribution, or sometimes called the equilibrium distribution, is where the number going from A to B equals, or it should be where the number leaving a state, this is a better definition for the general case, where the number leaving the state is equal to the number entering the state. Okay, and this for all states. Okay, so the stationary distribution occurs when, for every state, the number leaving is equal to the number entering. Right? I think that makes sense. And what this turns out to be is that, so if we write it, if we write kind of the distribution in the form, okay, where you have a row vector for the current distribution times the transition matrix P, is equal to kind of the next distribution. So then this, you know, P has the property where row sums equal 1, okay? So if the row sum equals 1, then the stationary distribution will be proportional to kind of the first eigenvector of the transition matrix. Well, let me see. Is it always going to be the first? It will be the eigenvector of the transition matrix, first eigenvector of all positive values. I think maybe I should say of all positive values. Okay. Or all non-negative, I should say. All non-negative values. Okay, first eigenvector of all non-negative values of the transition matrix. Okay. And in the two-state case, it's easy. If you've got then it will be the stationary distribution pi will be equal to P21 divided by P12 plus P21 comma P12 divided by so that, you know, if you so e.g. if, you know, we had 0.7, 0.3, 0.1, or what did I have? 0.7, 0.3, 0.4, 0.6. I think this was the example I had. Then the stationary distribution will equal basically 0.4 divided by 0.4 plus 0.3, and 0.3 divided by 0.4 plus 0.3, which ended up being 4/7 and 3/7. Yes, question?
So the diagonal entries are totally irrelative to the pi?
No, because the diagonal has to be, this entry and this entry have to add up to 1.
Oh.
Yeah, okay. they don't directly show up in here, that's true, but there's an implicit thing that, you know, whatever this is affects the diagonal because they have to add up to 1. Okay, so so this is what we have, and you can verify this, and you can do the math of the eigenvectors and stuff. All right. Okay. So, you know, all of this, obviously, we're going to have to deal with things that are more complicated than 2 states. And so, again, the ultimate goal, the big picture idea is we want to draw a sample, right? We want to draw a representative sample from some distribution. Okay, and this process of drawing the representative sample can be rather tricky, right? If you've got some kind of complex thing or something, if it's high dimensional, then doing some kind of uniform sampling is not going to work out that great. Okay, I'm going to close the poll here. So we want to draw a representative sample from some distribution, and it might be tough to do this. Okay, could be hard. And so one way to try to get one is by using a Markov chain where the stationary distribution is equal to, has the same distribution as the target distribution that you want, okay? If we can design a Markov chain is equal to the target distribution, then we can simply draw values according to the transition probabilities. Okay, so this is, in this contrived example, right? So if our target distribution is, 4/7 A and 3/7 B, so this is our target distribution, then instead of drawing from this directly, okay, which is very easy for us, but we're going to pretend that it's hard, okay? Instead of drawing from this directly, okay, we will run a chain with P equal to 0.7, 0.3, 0.4, 0.6, meaning, you just start with, some letter A, start with A, and then you say, basically, return, the next step will be either A with probability 0.7 or B with probability equal to 0.3 or something like this, right? And then and you go from A and then, whatever. Maybe you end up with A again, and then you just transition ... And then at the end, you take a look at all of the A's and all of the B's that you have, and 4/7 of them should be A and 3/7 of them should be B. Okay. Is that okay? So it's kind of like, I don't know. All right, so we want to get a transition matrix whose stationary distribution looks like the thing that we want. Okay. All right. So that's what we want, and I'm going to introduce something called the Metropolis Algorithm that achieves this. But I'm not going to tell you, like, I'm not going to try to like derive it. I'm going to just explain it and then try to show you that it does work. Okay. All right. So now I will introduce the Metropolis Algorithm. Okay, and we'll do this by way of example, and I'm going to use the example in Chapter 7 of the Doing Bayesian Data Analysis textbook, the puppies textbook, okay? So this is Chapter 7 of Doing Bayesian, what is it called? Data Analysis. All right, and so we're going to say there's some island nation. Island nation with, I think we said 7 islands. Yeah, we're going to have 7 islands. And in a row. All right. All right, this is all right, so these are the islands. 1, 2, 3, 4, 5, 6, 7. Okay. And in this silly example, okay, so there's a politician who wants to kind of campaign at the different islands, and he wants to spend his time at each island proportional to the number of people living on the island, okay? Wants to campaign and wants to visit each island proportional to the population of the island. Okay? That is, if the island has a high population, he wants to visit that island many times, and if it's low population, few visits, okay? Now, we're going to say the politician is not able, for whatever reason, cannot find the populations of all the islands all at the same time, for whatever reason, okay? So the politician does not know the population of all the islands. This is a contrived example, okay? Okay. So we can't just start off and, you know, sample directly, okay? So this is kind of like we're not able to just sample directly. Okay. But what the politician can do is he can call up an island, talk to the mayor of the, I don't know, whatever, king of the island, and say, what's the population of your island? And figure that out, okay? So we are able to, you know, call up one island and find out its population, okay? But we can call one island and find its population. Okay, this is very silly, but all right. And to just kind of make things easy for us, we will say the distribution is, we'll say so we know, the politician doesn't know this, but we, being all-knowing, we know the populations, okay? All right, and the populations are, Island 1 has 1 million, Island 2 has 2 million, Island 3 has 3 million, so on and so forth, up through Island 7 has 7 million, okay? For a total of 28 million people on the island, okay? In the nation. $28 million in the nation. All right, is that okay? I guess this is a big country, but that we don't know about. All right. So this is how this is what we will do. Okay. We start on an island. So this is basically the algorithm that the politician will use. Okay. So, we start on some island. Okay. Then we flip a coin. Okay, if it is heads, we propose going to the island to the right. We'll say we start on some island, let me just check the notation that the book uses, theta. Okay. Okay, we'll start on some island theta, and if it lands heads, we propose going to the island to the right. In this case, theta plus 1. And if it's tails, we propose going to the left. Okay, in that case, that would be theta minus 1, right? Then we, so this is proposing, okay? Then we call the mayor of the proposed island, or governor, or whatever. Governor of the proposed island. And get its population. Okay. And we compare this to the population of the island that we're on now. Okay. All right, so if the proposed island has a larger population, we will travel to that island for sure. So if the proposed island has a larger population, we will travel to that island, okay? Because we say, oh yeah, it's a bigger island than ours. We want to make sure we get more visits at these big islands. Let's go, okay? On the other hand, if the proposed island has a smaller population, okay, then we have to do a little bit of extra thinking. We don't want to say, all right, it's a smaller island, so we're not going to go at all. We want to say, all right, we do want to visit, but we only want to visit kind of with the relative to its size, right? So it's smaller, so we're not gonna go there all the time, okay? And so the amount we're gonna visit it with a certain probability. Basically, we're gonna draw a random number from 0 to 1, and the probability that we will go to the smaller island will be the ratio between its population and our island's population, okay? So if the proposed island has a smaller population, we will visit it with probability equal to basically small population divided by current population. Okay? So basically we have to draw a random number from 0 to 1, and if that number is smaller than this ratio, we'll go to the little island, and if that number is bigger, we won't go to that island, okay? So basically we draw a random number between 0 and 1. Okay, and we'll say if u is less than kind of the ratio, we go, and if u is greater than the ratio, we stay put. Okay, and that means we'll just do another visit, maybe like hold another campaign event at our current island. Okay, so we'll propose the next island, and maybe we go, maybe we don't. Okay, all right, is that okay? So let's try this out here. Okay, so let's say our initial state is we are on island 4. Okay, so I got 1, 2, 3, 4, 5, 6, 7. And so right now, our total probability is like this. Okay, so initial state, we're on island 4, so our distribution is going to be 0, 0, 0, 1, 0, 0, 0. Okay. Okay. So then the next state, okay, what is going to be our probability distribution? All right, so if we're at island 4, if I flip a coin, what's the probability I flip a coin and it ends up heads? 0.5, okay? And if it lands heads, then I'm proposing island 5, and if I propose island 5, I will for sure go to island 5, right? So, okay, so if I flip a coin and get heads, then we propose island 5, And island 5 has a bigger population than 4. So we go for sure. Okay, so then the probability of going to island 5 is 0.5. Okay. On the other hand, I have probability 0.5 of proposing island 3. Okay. And what is the probability I go to island 3 if I propose it? Okay. So if proposed, I go to island 3 with probability equal to 3 over 4. It's the island 3's population divided by island 4 population. Okay? Which means, what is the probability I will stay at island 4? 1/4 if I propose island 3. And I have probability 1/4 of staying at island 4. Okay? So basically, the probability distribution, so this will total out to be 0.5 times 1/4, which equals 1/8. And this will be 0.5 times 3/4, which is equal to 3/8, or 0.375 and 0.125. Okay, so the probability distribution on the next state will be 0, 0, 0.375, 0.125, 0.5, 0, 0. Is that okay? So this is 1, 2, 3, 4, 5, 6, 7. I just want to make sure from our initial state to our next state. So this is the probabilities where we end up, right? So if we always start at island 4, and then, you know, where am I going to be the next day? This is basically the probability distribution. Okay. So this represents basically the transition from going to from island 4 to the other islands, right? So this is basically the this is equivalent to the 4th row of our transition matrix. Is that okay? All right, so let's, I don't think we'll make the entire transition matrix, but we can imagine, I think I'll leave this as part of your next homework assignment, is we can have a transition matrix for all 7 islands. Okay. So we got from island 1, 2, 3. So this will be our from 4, 5, 6, and 7, and this will be our to island 1, 2, 3, 4, 5, 6, 7. Okay, and so we said if we're at island 4, there's no possibility, right? Because we can only propose the islands that are adjacent to us. So there's no possibility to go from island 4 to island 2 or from island 4 to island 6. And we said we will go to island 5 with probability 0.5 and we will remain at island 4 with probability 0.125, and we will go to island 3 with probability 0.375. Let's pretend we start at island 1. Okay. If we start at island 1, I will go to island 2 with probability what? Not with probability 1. I'm still flipping a coin. I flip a coin, and if it lands heads, I will propose island 2, and I will go to island 2 for sure, right? So I'm gonna just so this is coin lands heads with probability equal to 0.5, okay? And then that means go to island 2 for sure. All right, and then it could land tails with probability 0.5, okay? And if it lands tails, I would propose island 0, okay? Which doesn't exist. So effectively, island 0 has a population of 0. And so I would go to island 0 with probability 0 times 0.5, and which means I would remain at island 1 with 1 times probability 0.5, okay? So this means landed tails with probability 0.5, okay? We propose island 0 with population equal to 0. So we do not go to island 0. Okay, and then if we start off at island 1, we cannot end up at islands 3, 4, 5, 6, or 7. Okay. And you can imagine filling all of these out. And similarly for island 7, let's think about this. All right. So if we start off at island 7, I cannot end up at islands 1, 2, 3, 4, or 5 in the next turn, right? Okay. What's the probability I end up at island 6 if I start off at island 7? So that first I have to flip tails, right? With probability equal to 0.5. And then we're proposing island 6. And what's the probability I actually go to island 6 if I'm at island 7? And then we will go with probability what? 6/7, okay? Which means the total probability will be equal to 0.5 times 6/7, or 3/7. Is that okay? And then over here, well, we know the row has to add up to 1, so we know it has to be 4/7. But basically, this is going to be the combination of basically the 1/7 times a half that doesn't go to island 6, right? We proposed island 6 and we didn't go, and that's going to happen with probability, I guess, 1/14, okay? So this will equal the sum of basically proposing island 6 and not going, plus the probability of proposing island 8, which doesn't exist, and not going. okay, which is going to be equal to basically 0.5 plus 1/14, which is equal to 4/7. Is that good? And if I asked you to, well, I will, in the homework to fill out, in the next homework, to fill out the rest of the transition table, we can do that, right? Okay. I think we run out of time for today, but we'll continue. We'll take a look at this again on Monday, and then we'll generalize this so it's not just 7 islands, but possibly continuous, not possibly, to a continuous distribution and whatnot.